Hi, welcome to the first video in a series of videos I'm putting together concerning my book, The Shape of Space. The first series is going to be on linear algebra, and I'm going to give you a few preliminaries on that in this video. I'm also going to talk about the overall series on the next slide, just to give you a perspective of what's to come. So on this slide, I have an overview of the entire video series. These are listed here are the sections of my book, and for each section I'm going to have a series of videos. The first series of videos will be on linear algebra, and then we'll have follow-ups on matrices, matrix calculus, something called the Einstein notation, which is used for tensors, non-negative matrices, which we'll use to talk about Markov chains, and then least squares. So there'll be quite a few videos coming, and as I say, this very first video is just going to focus on some preliminaries for linear algebra. In my book, The Shape of Space, I assume the reader had familiarity with basic matrix operations as well as how to solve a system of linear equations. However, I thought for this video series I would at least give a refresher on some basics concerning matrices. So I'm kind of still assuming you've seen this before and you're looking at this more in terms of a review. If you've not seen it before, I'll put a link in the description where you can maybe get a little bit more information on some of the basics here. But let's start with the simple operations, scalar multiplication and addition. So we have here, I'm pointing to a matrix. Just to remind you, going this way horizontally are the rows. So there's 3 rows here, row 1, row 2, row 3, and then the columns go vertically, and there's column 1, column 2, column 3. They're normally numbered from 1 to 3 and so on, although there's some exceptions to that. If you want to add matrices, they need to be of the same size. And in this example here, we have 2 matrices, but we also multiplied this one on the right by 3. So when you multiply by a scalar, basically just a number, you have to multiply every element in the matrix by that number. So we've going from the first line to the second line, we didn't do anything to this matrix on the left. We multiplied everything in the matrix on the right by 3. So you can see we have -3, 6, 9, and so forth. And now we can add them. And the way you add is like terms in the same position are added. So you have the 1 and the -3, and you get a -2, 2 and 6, 8, 4 and 9, 13. You go down to the second row. 3 and 6 is 9, 2 and 0 is 2, 5 and 21, 26. And so on. So that's quite basic. And we could also do subtractions. It would work the same way. If we had a negative sign here, we would just negate everything in this matrix, multiply by -1, and then add them together. Or we could have multiplied by a -3 up here, and then again do the addition. So this is the most basic of the matrix operations. And as I say, hopefully this is just a review for you. Matrix multiplication is a little bit more complex. It's not what you might think. It's not a matter of multiplying the terms in the same position, but rather multiplying a row times a column. So in order for this to work, we need to have the number of columns for the matrix on the left be the same as the number of rows for the matrix on the right, which we have here. And then the result is you take the number of rows for the first matrix and the number of columns for the second, and that gives you the size of your output here. So the way you do this, let's just figure out this -1 first here. We take the first row times the first column. We multiply the 2 times the 1, and then the 1 times the 2, and the -1 times the 5. and we add those together. So we get 2 plus 2 minus 5, and that gives us a minus 1. Then to get this here, top right, we multiply the 2 times the minus 1, it's minus 2, 1 times 3, and we add those, and then of course the last one is minus 1 times 0. So we just get a 1 here. We can do the bottom left. You have 3 times 1, 2 times 2, plus 0 times 5, so that's 3 plus 4, 7. And then finally it's the second row times the second column, and you get minus 3 plus 6 plus 0. And that gives you a 3. Okay, so that's, if you haven't seen that before, you may want to try some examples on your own just to get that in your head. But that's how you do matrix multiplication. There's different cases for solving a system of equations. One case is where you have a unique solution, and that's what I'm going to show you first. So we have 3 equations and 3 unknowns here at the top. And the systematic way of doing this is to strip off the coefficients and put them in a matrix, as we've done here. You can see here 2, minus 1, 3, 4, so forth for the second and third row. And so the first column represents the x, the second column represents the y, and the third column represents z, and then the fourth column is just the right-hand side here. And then we can do operations that don't change the solution to the overall system. So we can add one row to another, we can subtract the row from another, we can multiply by a constant. All those are possible, and we will do that with the goal of isolating each variable x, y, and z so that we can just read off the value. And that's what we have here at the last step. We can read off x equals 2 over 11, for example. So I'll go through this, getting us to our final solution here. So the first step is to multiply the first row by 1/2 in order to get a 1 here. So I've done that, and you get 1 minus 1/2, 3/2, 2. And then nothing else has changed. So going from here to here, all I've done is multiply the first row by 1/2, and we have an equivalent system of equations here. Then we want to get a 0 here and here. So we multiply the first row by minus 3 and add it to the second row, and we get this here. And then we subtract the first row from the third row, and we get this here. So we get 0, 3/2, minus 1/2, and then 2 from 2 is 0. Okay, then the next step, and again, this is equivalent to this. The next step is to get a 1 here in this middle term. So we multiply by minus 2, and we get 1, 7, 10. No other changes in going from here to here. Again, this system is equivalent to this. Then we want to get a 0 here, so we multiply by minus 3/2 and add this second row to the third. And we get this here. We can reduce this to 11 when you do the cancellation, dividing the 2 into 22. And we want to get a 1 here, so we divide by 11 minus 11, and we get 15 over 11 here. That's the only change going from here to here. Again, in each step we have equivalent set of equations. Then from here we can go either way. One way is to take we already know what the value of z is now. It's 11 over 15. So we can plug it into the reduced second equation, which is y plus 7z equals 10. Plug in 15 over 11 for z here, and then solve for y. And then plug in z and y into this first equation and solve for x. Then the other method is just to continue with the matrix format, where we take 7 times this last row and add it to the second row. We get this, and then use these 2 rows to eliminate this here, which I've left out the steps, but it's basically going in the reverse direction of the elimination that we've done here. And again, we've isolated all the variables x, y, and z, and we get our solution. So you want to check this by putting in x, y, and z into each one of these equations to make sure they add up correctly, which I've done. Normally, you would use an online application. There's many. If you just do a search, an internet search on solving systems of linear equations, I'm sure you'll find something there. Okay, so that's our first example. We'll have a few more. Another possibility for a system of equations is to have no solutions. We have an example of that here. We have two equations, two unknowns. We put the coefficients into a matrix as we've done before. We already have a 1 in the upper left, and we want to get a 0 here just below it, so we multiply -2 times the first row, add it to the second, and then immediately we see a contradiction here. We get 0 equals 1. That means that these two equations don't have a common solution. And we can see that if we do a little bit of analysis here, if we take the first equation and we solve for y, putting it in the slope-intercept form, we get y equals -1/2 x plus 3/2. So the slope of this line is -1/2, and it intersects the y-axis at 3/2. And then we take the second equation, divide by 2, and then solve for y. And you see we get the same slope, but the intercept is different. So basically these two lines are parallel, which confirms our discovery here that they don't intersect. The third example is where we have an infinite number of solutions. It's known as an underdetermined system, and underdetermined in the sense that you can't determine a specific solution. There's an infinite number. So we have two equations and three unknowns. We put them into our matrix format here. We get a 1 in the first row by multiplying by 1/2, which I've done here. Haven't touched the second row yet. And this is equivalent to the first system. And then we want to get a 0 in this position here where the 3 is. So we take -3 times the first row and add it to the second row, and we get this. Then we want a 1 here, multiply by -2, and we get 1, 7, 10. At this point, we aren't able to isolate the three variables, so we make note that y equals 10 minus 7z from this second row, and we plug y into this equation here. And then we get x in terms of z when we plug in y, and then we have z here too, 3/2 z. And we solve that, and we eventually get x equals 7 minus 5z. And so our solution set, x, y, and z, is of the form x equals 7 minus 5z. I put that in here for x. Then substitute in 10 minus 7z for y, and then just put z in here. Z is the free variable, and we could have made it x or y, but the way we solved it here, we made z the free variable. And then we can break this into two vectors. One was the constant, 7, the 10, and basically the 0 plus the z. So we get this vector. And then the terms that have a z in it, and we factor the z out of it, and we get z times -5, -7, and 1. And so our solution is the straight line in three-dimensional space going through the point 7, 10, 0, and in the direction of the vector -5, -7, and 1. There's one more case, and that's called an overdetermined system. You see here where we have more equations than unknowns. We have two unknowns and three equations. And we can write that in a matrix format, AZ equals B, where A is the coefficients on the left, 1, 1, 1, 2, 1, 3. Z is the variables we're looking for, and then B is the what we have on the right. And there's no exact solution to this, but what we can do is find a value for z such that it minimizes the difference, the norm of the difference between az and b. And that's actually called the least squares problem. We're not going to solve it here. In fact, it's the very last series of videos in this collection of videos that I'm preparing. But I just wanted to put out the final case here in terms of systems of equations. So if it didn't quite ring a bell with you, we will get to it, as I say, much later in the video series. This is really a minimization problem where you can't find a solution, but you try to find the best value of z that sort of minimizes the difference between az and b. Okay, one last preliminary, and this is probably the hardest one to work through in terms of the computations, but that's finding the inverse of a matrix. And let's say we had it has to be a square matrix. So let's say we had the matrix here on the left, 2, 1, 1, 0, 3, 1, 1, 2, 2, and we wanted to find what matrix, when we multiply times it, gives us what's called the identity matrix. That's the matrix 1, 1, 1 along the diagonal and zeros everywhere else. And the way to do that is to use the elimination, the Gaussian elimination, going to an upper triangular form, basically this form here, and then reverse it and going and getting zeros on the top. So it's sort of what we've seen before, but it's rather computational intensive. So let me go through a few of these steps. I might skip over a few of them and leave it to you to read through the details, but just to make sure you understand the idea. So if you want to find the inverse of a square matrix, and if it was 4 by 4, you would have you would have an identity here that's 4 by 4, but in this case it's 3 by 3. So you put the matrix on the left, the identity matrix on the right, and the goal is to do row operations to eventually get the identity on the left and what turns out to be the inverse of what you started with on the right. So that's the goal. So you start by getting a 1 here, multiply this first row by a half. We get what's up here. We didn't touch the second and third row. Then we already have a 0 here, but we want a 0 here, so we subtract the first row from the third row, and we get what we have here. We didn't touch the second row or the first row for that matter. We just subtracted the first row from the third. We get this result. Then we want a 1 in this position, and so we divide this second row by 3. We get this here, and we didn't touch the third row yet, but we'll take a minus 3/2 times the second row and add it to the third row, and we get this for the third row. So this is actually, earlier I said this was upper triangular, which is true, but we actually got to the upper triangular format one step before that, which we are here. So we're almost done. Now we need to eliminate the 1/3 from here, make that a 0. So we take minus 1/3 the third row and add it to the second row, and that knocks that out, and then we get 1/6, 1/2, minus 1/3. And then we take minus 1/2 the third row and add it to the first, and we get the result here. I'll leave it to you to check the computations. And we're almost done. We just need to eliminate this 1/2. So we take minus 1/2 the second row and add it to the first. And we get a 0 here, and then again, I'll leave the computations to you, but you get this here. So what you might want to do is just to practice your matrix multiplication. If you multiply this matrix here on either the left or on the right of the matrix that we started with, you should get 1, 0, 0, 0, 1, 0, 0, 0, 1. It's a little bit involved because you have fractions here, but If you need some practice, you may want to try that in terms of practicing your multiplication. Okay, so those are the preliminaries for the subsequent videos I'm going to present, on linear algebra. I kind of assumed this in my book that the reader knew these things, but I thought for the video series I would at least give you a little bit of a refresher on some of these basic operations involving matrices.